Welcome to the lecture for section 6.5 in the textbook on the distribution of the sample mean x bar and also on the central limit theorem. Rather than talk in terms of theory, we're actually going to present this topic by looking at an extended example. Suppose someone goes fishing one day and comes back with fish that have these weights in pounds. Now we could get a sense of the what this distribution looks like by making a dot plot. So let's do that first. We placed a dot on the x-axis every place that we have an observation or a data point, and we can observe some things about this distribution right away. We see the bulk of the data, for instance, is down here on the left-hand side, and we have a couple of look like outlying values off to the right. So this is an example of a distribution that's pretty strongly skewed to the right. There's a long tail off to the right-hand side. Bulk of the data is grouped down onto the left-hand side. Now, let's suppose that with these 6 fish, the owner decides he's going to package up 3 of them and give to a friend. Now, we can see the weights of the individual fish here, but it would be interesting to know what, of all the possible ways of selecting 3 fish and putting them in a box, what would the average weight be for a fish that was put in a box? Well, what we could do here to help us keep track of this a little bit would be to give names to each one of these weights. We could call this first one A, B, etc. And that would be a guide for us in how we might select these weights, so we could think about the letters rather than be writing numbers all the time. And if we do that, what you'll find out is there are these possibilities for grouping the fish 3 at a time. And then we could replace each one of these letters by the corresponding weight. If we did that, then each time we took one of these possibilities, say we gathered up the first 3 fish, those would be the lightest 3 fish, right? 4.55 and 5.5, that would have an average, which in this case would be 5. And that's been recorded over here as well. On the other hand, if we think back to our original data, these were listed in numerical order, so the sample of size 3 that would weigh the most would have the 3 heaviest fish, 6, 8, and 10. And you could see straight away that 6, 8, and 10 has an average of 8. And that's down here in our table. If we choose the last 3, D, E, and F, we get 6, 8, and 10 in our sample, and that has a weight of 8. Now, just as we made a dot plot of the original data, we could think of this as sampling the data 1 at a time. So we have a sample of size 1 along here on the x-axis. We could do this again for, say, samples of size 3. So on this row right here, I'm going to do a dot plot for samples of size 3, but now I'm not going to plot these individual points. Those we already know what they are. They're right here. I'm going to plot these average weights along here, and we're just going to fill that in quickly. So here's what we get after we plot all of these averages. These are averages for samples of size 3. All the possibilities have been listed, and you can see that something interesting happens to the graph. Well, first of all, there's a whole lot more averages than there are just individual measurements, and that is because what we're thinking about is we are taking all combinations out of 6 objects, taking 3 at a time. This number is quite a bit larger than 3. As a matter of fact, if you remember the formula, that's 6 factorial over 3 factorial 3 factorial, which we could factor out this way, canceling out those 3 factorials. 3 factorial is equal to 6. Those cancel out. And so we have a total of 20 samples of size 3. There's quite a few things in this list, and therefore quite a few more dots up here. But these are all the ways that the owner could package up 3 fish, and the average weight of the 3 fish in the box would correspond to these dots. Now, when we just think about this, what is the lightest possible package you could make? Well, it would, of course, be by taking the lightest 3 fish, and across here, the minimum average weight is 5, whereas the minimum single weight is 4.5. In the same way, if we took the 3 heaviest fish, 6, 8, and 10, took the average of them, we'd get 8. The heaviest average weight of 3 is 8, whereas the heaviest single weight is 10. So what's happening here is everything is shifting towards the middle. But more importantly than that, whenever we have an outlying value, that gets that effect of shifting towards the middle quite a bit more than something that's more near the central tendency of the data in the first place. The consequence is this. First of all, we've gotten more dots. Secondly, those dots have moved toward the middle. And thirdly, the heavy skew that's in this data is beginning to disappear. And this doesn't look so very far from being symmetrically distributed here. There's another thing that you might guess, but you wouldn't know exactly unless you did the calculation. If we take the average, the mean of these original data points right here, we will get 6.5. And that, on our graph, is right there at that point. It turns out that if we take the average of all of these values here, of these averages of samples of size 3, the mean value of the x bars is also 6.5. The mean of this distribution is also 6.5. Well, why don't we try that again for another sample size? Suppose we were going to take, say, 5 out of the 6 fish and put them in a box. What would the mean weight look like for all the possible ways of choosing 5 out of these 6 fish? Well, first of all, if we were going to select 5 out of the 6, that is exactly the same as choosing 1 fish to leave out. So since we only have 5 fish to choose from, there's exactly 5 ways to leave out 1 fish, and therefore there are 5 ways of getting a sample of size 5. I've listed them here with letters. Replace those letters with numbers, and here are the averages that you get by taking 5 of the fish at a time rather than by taking 3. There are quite a bit smaller number of averages, and that's because if you take 6 things, choose 5 at a time, you don't get many options. Out of 6 things, the number of ways to choose 1 is 6. So there is exactly 6 different averages here. Well, let's graph those. Okay, we've graphed the means from the samples of size 5, and we end up with this graph right here. And what you notice straight away is that this effect that we had at first has continued. This distribution is pulling in closer and closer towards the central tendency of the data, and it probably is not a surprise that if we were to compute the average of all of these numbers here, you get, once again, a value of 6.5, which on our dot plot would lie right here. So we noticed the following things happening as we start grouping up the data into larger and larger subsets and computing the average. The first thing is, right at first, there's a proliferation of these dots. We get a lot of samples, and then because of the fact that we started with a small population, the number of dots does shrink down again. Secondly, these distributions continue to pull in towards the center from both sides. And thirdly, this effect down here of having outliers, that is pretty well completely gone up at this point. This is not perfectly symmetric, but there's no hint of an outlier in this. The general effects then are these. First of all, the mean stays the same. Secondly, the variability is dramatically reduced. And thirdly, outliers and skew tend to disappear as the sample sizes get larger and larger. As a matter of fact, this is always going to be true. If we start with a population and start taking larger and larger samples and compute the means of those samples, two effects are always going to occur. First of all, as the sample size gets larger, the average of those samples is going to be less and less variable. Secondly, it's going to have a more symmetric distribution. And thirdly, the mean of the sample means is always going to be the mean of the original distribution. Now, all of those ideas are summarized in actually more than one theorem, but I'm just going to lump it all together and call this the Central Limit Theorem of sampling. It tells us this: given any large population of single values x, so we started with kind of a small one, but the quantitative effects we're going to note here really only work when the sample is quite large, or rather when the population is quite large. Given any large population of single values x that have some mean mu and some standard deviation sigma, if the sample size is large enough, then three things are going to happen. The first is this: x bar itself is going to tend toward having a normal distribution. Now, we sort of see that effect here. You can't tell that it's normal, and in fact, you don't get the effect for a small population. But you can see this: the skew is disappearing. It's starting to look more and more symmetric, and that will occur to the point that you actually have not only a symmetric distribution, but a normal one. So the distribution of the sample means x bar will be normal, or approximately normal for a large enough n. The mean of all the x bars is going to be the mean of the original distribution, and the standard deviation of the x bars is going to be the standard deviation of the original distribution divided by the square root of n. We are expecting this kind of effect because the standard deviation, the variability, does not stay the same as the samples get larger, right? If we look back at our graph, what we see is the variability tends to get smaller and smaller. As a matter of fact, we could extend this project one more step if we wanted to. We could go all the way up to a sample of size 6. Now, if we took a sample of size 6, then we would have only one observation, right? We'd take everything, and its mean would be 6.5, just as we noticed that the mean of all these were 6.5. And so we've really compacted our distribution down to a single point. It doesn't have any variability at all anymore, and that's to be expected. As the sample size starts getting larger and larger, the variability of the x bars becomes smaller and smaller. Eventually this shrinks to a point and goes away completely. Now, statisticians have a symbol that they sometimes use that summarizes all of this for us. And here it is. This is how we're going to translate it. We're going to start with a large population. It has a mean and a standard deviation. We're going to start taking samples that are larger and larger out of that original population. For each one of those samples, we'll get an x bar. Now, if we take lots of samples of a particular size n, we will find out that the means of those samples of that particular size are normally distributed. That's what the cap n means. The x bars are normally distributed. They have a mean of mu, the mean of the original distribution, and they have a standard deviation that's smaller than the standard deviation of the original distribution. As a matter of fact, it's that original distribution's standard deviation divided by the square root of n. So x bar is normally distributed with mean mu and standard deviation sigma over root n. Now, one last thing that we might want to mention here is this. Whenever we start with a population, we're drawing out of it some smaller group, which is our sample. Now, there is a mean of this original population, which we're calling mu. There is a mean of this sample, which we're calling x bar. Now, we've seen the effect ourselves. The x bar of a single sample does not have to be the mean of the whole population, which in this case is 6.5. These means can differ, but the average of all these means must land here, 6.5, which is the standard, which is the mean of the entire population. So these x bars are going to approximate the mean of the whole population. Now, that difference, x bar, the difference between x bar and mu, you can think of that as an error. This doesn't match that exactly. It has an error. We say that the standard error of x bar is sigma over root n. And what we mean is that the standard deviation of these x bars is this value right here. So sometimes these are less than mu, sometimes they're more than mu, but they have a distribution, and a standard deviation is that value right there. All right, so all that is a good description of the idea behind the central limit theorem, but what it doesn't tell us is how to do calculations. So there is a formula that you'll find on your formula sheets and in your textbook that says this: z is equal to x bar minus mu over sigma over root n. This is a formula we are going to use to be able to compute probabilities and z-scores, things like that. Once again, I'm going to communicate this by looking at particular examples. So you want to look at the homework help for section 6.5, and I'll be showing you exactly how to use that formula and how to solve the problems.